Welcome to the Mentored Engineer. In this video, we're going to talk about using parallel links to maintain level in a system. Okay, so we already kind of briefly went over parallel links, and there's two fascinating things about parallel links. One is that the placement of the load has no effect on how hard it is to lift up the load. So if I'm lifting 1,000 pounds, or in this case 100 pounds, right over that link versus way out here, my cylinder force does not do anything more. You might have some more friction to overcome, but that's a small potato type thing. And I'm going to show you that first by proving that the placement of the load does affect something, but it doesn't affect our cylinder. Okay, so if I look at this, and for my first case, I'm going to put 100 pounds right over this pin, and I'm going to figure out what the tension is in that member right there. Okay, so do my static sum of the forces. So 0 equals 100 times its moment arm from A, which is where I'm summing the moments, divided by the distance between the bars, which is 10, and then multiplying it by the force in the link, and then solving for the link force. And 100 times 0 divided by 10 is still 0. So there's no force in that link. It's kind of just on along for the ride, and it's just making sure that that maintains level. All right, so if we move it out to the end, I've now got 100 pounds times 120 inches divided by 10 inches, and my force will be 1,200 pounds. So I've increased that quite significantly by moving out 120 inches. But what doesn't change is how this compression member does. And it's a member, it is not a link anymore, because I am using it to lift something. So I can go through a lot of the statics, but this one equation right here tells you everything you need to know. All right, so if I look at this as a beam, I'm actually going to redraw it for you here. All right, so it's a fixed beam, and it's holding a load here. Okay, now I have redrawn my coordinate system in a very unusual way, but the X is in line with the links, and the Y is perpendicular to that. Okay, so if I look at A, or if I look here at BB, and I'm going to draw my coordinate system the same. All right, I need a force times a distance. All right, so my distance here I've said is 40 inches. All right, and my force is simply going to be the cosine of 60 degrees times the load, which is 100 pounds. I end up with 2,000 inch-pounds. Okay, now this beam doesn't change in length. It's still the same 40 inches. It's still going to lift the same 100 pounds over here, and my angle hasn't changed. So I still have the exact same equation. On both sides, I get 2,000 inch-pounds that I have to lift right there. And I just size my cylinder according to that. But it's fairly simple that, my cylinder force does not change when I move the load out. My tension link force changed, and the compressive force in that member is going to change. But that's one of the cool things about linkage is you can get away with a very small cylinder, especially if you have great geometry on it, lifting heavy loads. So the next thing about parallel links that you need to watch for and understand is which load is predominant. All right, so I may have a load here, and at some point the load may actually, let's say slide over this way, or just you're picking up something else. But I've now changed my the way I've got forces in here from I start off here. This link is going to be in compression, and this one's going to be in tension. And then if I move it to the other side, well, they suddenly switched. So now this one's in compression, this one's tension, and that makes a difference. I personally, try to maintain the loads on one side as much as I can. All right, and the way the reason that it matters is, let's just say here, we'll simplify this again. And we now know that we've got compression here, and we got tension there and tension there. All right. when I add in my cylinder, I want to attach it to the compression member. And the reason for that is this cylinder will also be in compression. All right, so I got compression. And what happens is my natural flow of stress will flow down here, and it'll say, hey, that's just about an equal amount of force here. It'll come down into my cylinder. And then I'll have just a teeny tiny bit left over coming into that pivot. So that pivot is not really doing much. It's holding its position, which is why we have it in the first place, but my force is going in a direction that I like. All right, if I do the opposite, and I put this on this side, what happens is I've got, let me do this in the other color. I've got compression here and I've got tension. All right, and that compression has to go somewhere, and what it does is it says, well, I can't go up there because that I can only take that much tension. It's got to go back to this point, back to this rigid structure right here, whatever it is, and it makes a U-turn. It's quite awful, and I end up with the tension force plus the compression force of the cylinder. So I've actually added a whole bunch to there. Now, if you have a case where it goes back and forth, you're going to have to deal with that. But generally speaking, you're going to have a primary load that's further on one side than it is on the other side. So at that point, you know, make sure you're biasing it to use the member that's in compression most of the time. All right, well, thank you for watching this episode of The Mentored Engineer. I hope you learned something. I hope you can apply it and use it in your daily use as an engineer. Thank you for watching.